Hey everybody. You can see on our screen today what we're going to do is we're going to go through and solve quadratic equations. Now I've called this quadratic equations 1 because I'm hoping that this is your dominant way or becomes your dominant way to solve quadratic equations. So we're going to jump into a certain type of situation today, and I hope this gives you a pathway to be able to solve maybe a more complex equation. Okay, let's jump in. Here we go. So what you see on your screen right now are examples of two quadratic equations. You'll notice in problem A, I have something that maybe seems relatively straightforward. Problem B may be a little uglier with the brackets. Can I just get us to focus in on one thing that's in common in both of those equations? You'll notice that my x, my variable, has an exponent of 2 in each case. So that's what makes that a quadratic equation. A quadratic equation is a formal way of saying an equation that has the highest degree being 2. So really all we're doing then is we're solving equations today that happen to give us variables with an equation 2, or with an exponent 2. Okay, now what I want you to do is I want you to zero in on the equation in A. And I want us to realize that that equation in A is just like every equation you probably solved in grade 9. You take a look and you notice that your variable is in one spot, and you should have like a two-step process to be able to solve that equation. Isolate the variable term, and then isolate the variable. I'm going to argue to you, you should have had experience with A in the past, but it wasn't common. And there is a little bit of a wrinkle that may cause you some indecision. So let's take a look at A, and I want to walk through with A how I hope we would solve the equation. First off, we want to make sure that we isolate the variable term. So that means we need to get the term that contains the variable all by itself. So we need to get rid of that minus 10. We should be okay to get rid of a minus 10, means I'm going to add 10, and there's my 45. Okay, this could be the process, though, that's going to cause you a little bit of a wrinkle. That is, in the past, you very rarely had an exponent on your x, on your variable. And so I just want you to imagine right now that that exponent was not there. There's no decision in your mind. For you to solve for x right now, you're going to divide out the 5. You have to isolate the variable, which means get it all by itself. That means the only thing attached to that x is the 5. Let's divide it out. But if I go back to what that equation is now, it's 5x squared. And you'll notice you actually have two things attached to the variable, and this can cause some indecision. Now, you have to get rid of that 5, but you also have to get rid of the 2. Which one do you get rid of first? Okay, I'm going to argue to you, mathematically, it does not matter in terms of solving the equation. But one way is going to be more complex than the other. So if I could give you a little piece of advice, I would get rid of the blue first. For me, the last thing I always get rid of is my exponent. And I want to show you what happens. If I was to follow through with the blue, that's me just recognizing the multiply by 5, so let's divide it out. Then that equation is going to become x squared equals, to get rid of a times by 5, I divide by 5, and 45 divided by 5 is 9. Now, if I'm going to finish it off and I get rid of the squared, the exponent 2, then I should be good that to get rid of a squared means I take a square root. But we have to remember that every time I take a square root, I get two answers, a plus or a minus. And now when I go to calculate that, well, I can calculate the root of 9, and the root of 9 is 3. Okay, you do a quick mental check and notice that if you subbed back into your original equation, positive 3 or negative 3, that statement is true. Okay, so the blue equation I'm hoping looks pretty straightforward, and actually I'm hoping it comes back to you from last year. But what about the green? Okay, I maybe misled you a little bit when I say like both mathematically will get you there. I 100% agree. One is going to have more work to do, that's the green, but also there's a huge risk for mistake. I'm going to go through now and I'm going to get rid of the squared and show a different approach. First off, I want to make sure that when we eliminate that squared, we eliminate it properly. A real common mistake would be to do this. Well, to get rid of my squared, I take the square root of the other side, and I know I get two answers, and you write something like that. Okay, I'm hoping that we can recognize that that green is incorrect. But we might not be able to recognize it because we would go along with the common mistake too. Maybe you can see that we actually didn't do the same operation to both sides of our equation. We made an error. Our equation is imbalanced. So what I want to do is I actually want to go back and just copy out that equation one more time so we can really nail down what we have in front of us. If we are good with that whole analogy that each side of my equation is a scale, and whatever I do to one side, I have to do to the other. That if I see right now that I have 5x squared on one side of my scale and 45 on the other, if I just eliminate that squared by taking the square root, maybe you can see I didn't actually do the same thing to both sides. Notice my square root operation is over the 45. But my square root only eliminated the squared on the left. What about the 5? So if I actually went back to where we were on that scale, I have a 5x squared on the left side, and it is equal to a 45. If I take the square root of both sides, then I need to take the square root of 5x squared, not just x squared. That becomes the wrinkle, and that is the common mistake. So if I eliminate my really, I don't know, scrappy drawing of a scale, and I just did that operation within my equation, the square root of both sides of my equation, that is now true. But unfortunately, when I now go to calculate that, I have the root of 5 because I can't calculate the square root of 5. I can take the square root of x squared and be just left with x. That, of course, is going to give me a plus or minus, which really should be represented on the line previous. And now I've got the root of 45. Okay, some of you guys might start to see that this equation just got a lot uglier. Don't worry, we can still solve it. I just have uglier numbers. I am in the process of isolating my variable. Look what's attached to my variable. I've got a root 5 that's multiplied. Well, that's no problem. To get rid of a root 5, I need to, a times by root 5, I need to divide by root 5. Well, now this does bring in some complexity, and I would argue to you it actually brings in some stuff that's maybe above our level that we're playing with. Luckily, we're okay to be able to reduce a radical. And so we should be okay to say, well, I could look at 45 and I know that 45 is 5 times 9. And so I could reduce the radical on top because I can take the square root of the 9, but I cannot take the square root of the 5. And I can simplify that down to plus or minus 3 root 5 over root 5. Maybe we can see where we go from here. I could now go and divide out my common factors of root 5 on top and bottom. And now I'm left with x equaling plus or minus 3. Okay, that's a lot more complex. And I'm hoping with that problem, we can see that your blue equation, that blue process, is so much more straightforward. That I would hope that just seeing that example really guides you guys to something. Let's look back. When I'm in the process of trying to isolate my equation, my variable, when there's a coefficient and an exponent on it, I would hope that everyone would choose to divide out the coefficient first. Deal with the exponent last. Okay, I'm hoping that that gives you a little bit of guidance and shows you the benefit to isolating that way. Okay, I need everybody to focus in on B now. I'm hoping B is a pretty automatic one for us, and also one that's a pretty straightforward check. So much so, I want you to pause the video now, and I want you to go through and try to solve B. Okay, pause the video, we'll match up in the end. Okay, we're back. So you take a look at B. I'm hoping we recognize the operations in the equation and that it's probably a pretty straightforward action for us to go ahead and expand in the 6. Then on the right side, we can expand in our 4. And really, you've got something that starts to look like the previous equation. Well, I've got 2x squared terms. I can try to isolate my variable term, which means I can collect them on the left. That does mean I have to get rid of a minus 72 on the left, so I can get rid of a minus 72 by adding 72 on the right. And when I add 72, I get a nice round number of 100. And now I come in on the last equation. Here's where I'm faced with that question now. What do I want to do? Do I want to get rid of my times by 2, or do I want to get rid of my squared? And I hope that I have motivated everyone to get rid of the coefficient of 2 first. So how do we get rid of a times by 2? We can divide by 2. And now how do I get rid of a squared? I take a square root. When I take a square root, I get 2 answers. We are not going to stop at root 50 because we can take a look and we see that 50 would be a 25 times a 2. And so we can take the square root of 25, but not the square root of 2. And there we go. So hopefully we're doing quite well with B, and that's going to be your motivation for today. Can you isolate your variable term and then isolate your variable? Okay, all I want to do for the rest of the day is throw some equations at you and allow you to get some practice working through isolating your variable. Okay, let's jump into a few more. Okay, what you see on your screen now, 2 more equations. I want you to focus in on question C, because you might notice something's a little bit different in question C than A and B. You don't have an x squared. So I'm hoping with that difference, you are not motivated to do something different, but rather you recognize your variable is in one spot. It's sitting right there. Why don't we just isolate it? Okay, I do want to draw to your attention one problem though. That after spending a little bit of time with your algebra, you may have been motivated to see the left side of that equation as a perfect square, and you would have said, hey, I've spent a lot of time expanding that perfect square. Okay, what if that instinct took hold? Well, on the left side then, you're going to end up expanding your perfect square, so squaring the first, multiplying them together, doubling it, squaring the last, and you're going to end up creating that equation. I want you to notice you really just created a problem for yourself. How do you isolate your variable now? Notice you now have unlike terms with your variable. That is, you have a single x term and you have a squared x. We cannot collect those together into one variable term. We have a problem. I can't isolate my variable easily. So I want to make sure that we are quite comfortable and quite aware that just because we see brackets, that does not mean we should expand. In fact, if we go back up to the original equation, I hope your instinct takes over. I'm going to highlight it one more time. There is your variable. It's in one spot. Why would you ever expand your brackets to put your variable in two? If you got it in one spot, just isolate. Okay, what's the first thing we got to get rid of? Well, you notice all the stuff that's attached to that variable. I have a times by 2 out in front. I have a subtract 3. And I have an exponent 2. Okay, one strategy that you can kind of follow is to work outside in. I'm hoping that what we actually recognize is everything inside the brackets just represents something that's missing. Like 2x minus 3 has a value to it depending on what x is. We just don't know what x is. So 2x minus 3, everything on the inside of the brackets could just equal like happy face. So really what that equation says is happy face squared equals 25, right? Something squared equals 25. And I hope we're good to see we could just eliminate our squared. You'll notice then if you look on the left side, you're getting rid of the operation that's most on the outside. So let me get rid of my little happy face and let us focus in on the original equation. Look at that red exponent. I can get rid of that red exponent. How do I get rid of an exponent squared? Well, that squared is on everything on the left side. So let's take the square root. And when I take the square root of everything on the left side, you'll notice my red squared is eliminated. Of course, that means I have to take the square root of everything on the right side to keep my equation balanced, and we're off to the races. Okay, I'm going to get rid of all of those colors up in the original equation and make sure we're good and going in our parts. So first thing, let's get rid of our squared, which means I take the square root, and when I take the square root, I have two possible answers. Okay, you would never have to show me that line. I would love it if you simply looked at it and said, well, the square root of 25 is plus or minus 5. Okay. I would maybe suggest the next line, though, but I'm also going to put it in orange because I wouldn't have to see it. But my next line could start to look like this. Well, to get my 2x all by itself, my variable term all by itself, I need to get rid of that minus 3. And to get rid of minus 3, I need to add 3. Now, you will notice that I chose to write that expression as 3 plus or minus 5, just because it's a little bit easier to interpret than the plus or minus 5 plus 3. You'll notice my orange actually has fewer operations written. So that's why I tend to put the positive value first. Okay, now what I want to do is I want to simplify the right side. So I always want to simplify everything I can. I'm going to end up getting two possible answers. I'm going to get 3 plus 5, which is an 8, or I'm going to end up getting 3 minus 5, which is a negative 2. Okay, I still have to be able to solve that. Well, this is where it can sometimes get a little awkward. The next line in your equation might end up being to get rid of your times by 2, because I need to isolate my variable. I need to get divide by 2. I just need to make sure that I divide both of those solutions by 2. So I'm going to end up getting 8 divided by 2, which is 4, or negative 2 divided by 2 is negative 1. And there's how I can solve that equation. Not too bad. You go through and you give me that solution, and you guys should be good. I did actually make an error there, though. That last line I would need to see. So if you're matching with my colors, that last line should have been in gold. You give me the gold lines, you've got a full solution. I do want to maybe draw your attention back to one line, though, and it's this orange one. That some people are not going to like writing down the gold line that follows. And rather, they would have liked to have isolated 4x before they dealt with the plus or minus. And so they may have chosen to put in a line where they said, well, I'm going to get rid of my times by 2, so I'm going to divide by 2 right away. And that's the expression that they're going to determine their values for x. Take a peek on that last orange line now, and you can calculate your two solutions. 3 plus 5, which is 8, divided by 2 is 4. And then 3 minus 5 is negative 2, divided by 2, negative 1. Some people like the orange lines in there. I'm going to flip-flop back and forth with regards to how we solve. Okay, I think you've got enough from that one to give D a shot. So I would like you to go ahead and try D on your own, and we'll see how we match up. Okay, pause it now. Okay, we're back. So you take a peek. What's the only difference I really did in question D from C? I've got that plus 7 there. So same thing. I am hoping we say, let's isolate our variable term, which means we have to get rid of any other term. Okay, first line in my solution then is going to be my 4x plus 2 squared, and that's going to equal 10. Okay, now I've got an equation that looks just like C. We should be off to the races. I want to eliminate that squared that's on the very outside. So in order to get rid of a squared, I need to take a square root. And when I take a square root, I know I've got two answers. There's my plus or minus. I cannot calculate the square root of 10, so I just leave it as root 10. Some of you guys might look at that and go, ooh, this one's uglier. And I might argue to you, it's actually easier when we can't calculate that square root. Let's watch. What would be my next step? Well, now I need to still isolate my variable term, which means I need to get rid of that plus 2. So I need to minus 2. I am now going to go through and I'm going to write the negative 2 out in front. Now, you may wonder why I do that, and I'm just going to slide my equation across. Really, it's to avoid this confusion. If I sloppily write down plus or minus root 10, and then write minus 2 to follow, do you notice that by the length of my square root operation, I almost made it look like the minus was underneath the root? And so that causes confusion. Okay, was the minus 2 supposed to be underneath the root, or was it supposed to be outside the root? Like, I'm not sure. And if I do choose to write that minus 2 afterwards, then I better be darn clear that it is just the 10 that is underneath that root, and that the minus 2 is clearly outside. And sometimes I don't know if I want to put that much focus. Notice in what I have in the gold. By me putting the minus 2 out in front of the root, there is no ambiguity. There's no indecision. That minus 2 is clearly not underneath that root. Okay, I cannot collect that negative 2 with the plus or minus root 10 because those are unlike terms. So now I need to isolate the variable. There is my variable, so what do I have to get rid of? I got to get rid of my times by 4. So I'm going to divide it out. I have 2 terms on the right side. I need to make sure that I divide the whole right side by 4. And there we go. Now, I do want to draw to your attention something that's very important. That we may take a look at that gold fraction on the right, and even though we recognize that we can't put the 2 and the root 10 together, that we may see a 2 on top and a 4 on the bottom and say, hey, I can reduce my fraction. I can divide a 2 out of both of those because a 2 goes into both 2 and 4. You can't. Be very, very careful. I'm going to actually get rid of the blue circles and just change that answer a little bit. That when I write down that old answer, look how many terms I have on top. I have 2 terms. Look how many terms I have on the bottom. I have 1. If I'm going to divide out a common factor on top and bottom, then it has to be a factor in everything. And you'll notice 2 is not a factor in root 10. Let's do our little factor tree. Yes, there may be a 2 in root 10, but that's not a 2. That's a root 2. So I cannot divide out a 2 from everything. Therefore, what you see in the gold is fully reduced. If you got down to negative 2 plus or minus root 10 all over 4, outstanding. Okay, let's give another few a shot. Now, okay, you take a peek on the screen now, and I think that we're at a point where we've discussed enough that you could go through and get solutions to these. Now, we might get some quirky things that pop up, some things we need to address, but otherwise, I think your instincts should be taking you down a good path. I want you to go ahead and try these on your own. Let's start off with E. Okay, pause the video now. Okay, we're back. So you take a look at E. E looks very similar to the last one. Let's go ahead and deal with it. That means my variable term is this whole term. It's separated by the minus 10. Get rid of it. So I'm going to have my 2 times x minus 3 squared. To get rid of a minus 10, I add 10. Okay, now I'm faced with a problem like equation A. I have a coefficient on my bracket and I have an exponent. I want to get rid of my coefficient first. If there's any hesitation, look back at your solution for A. Don't take the green path. So I now want to isolate my power, which means I want to divide out my 2. So that means that I'm going to have my x minus 3 squared. To get rid of a times by 2, I'm going to divide by 2. There's my 20. Now I'm still working, so I got to get that base all by itself, which means I need to get rid of my exponent. To get rid of an exponent 2, I need to take the square root, and when I take the square root, I get 2 answers, plus or minus. I'm going to take a peek to see, can I reduce root 20? Yes, I can, because 20 is 4 times 5, and so that right side could be written as 2 root 5. Take the square root of the 4 is 2. I cannot take the square root of the 5. The operation's left in. Okay, to finish off the problem, now we have to get the x all by itself, which means get rid of that minus 3. And so x is going to equal a positive 3 plus or minus 2 root 5. And because that root 5 is attached to that 2, I have unlike terms. I cannot collect the 3 with the 2. I am done. Nice. If we got down to that, I think we were doing outstanding. Okay, let's give F a shot. If E went well, you should be jumping in, giving it a full go. If we had a little bit of a hiccup on E in anywhere, then I want you to just pause the video, look over E again, look back at A through D, try to see some patterns, and then I want you to try F all on your own again. Let's use that one as another opportunity to gauge where we're at. Okay, pause the video now. Okay, we're back. So I'm hoping we see that F is just like E, just maybe the numbers get a little bit bigger. I'm going to stop putting all the colors in my solution, and I'm just going to work through that solution. Pretty straightforward. Okay, I want to get my variable all by itself, which means get that term all by itself. I need to get rid of any other term, which means I'm getting rid of a minus 45. That means I'm going to add 45. 99 plus 45 is 144. Okay, now I need to go through and I need to get rid of my times by 3. Well, to get rid of a times by 3, I am going to divide by 3. Well, I need to now take 144 and I need to divide it by 3. So maybe off on the side I have to write this down. I hope not. I'm hoping we can just do some short division. How many times does 3 go into 14? We should be good that we could take out 4 of those because 3 times 4 is 12. That means we have 2 left over that we're going to now put together with the remaining 4. How many times can you take a 3 out of 24? That is 8 times, and you did a little short division. Nice. Okay, we get to that point, and this should be looking very familiar. To get rid of your squared, you need to take the square root, and when you take the square root, you've got your 2 answers. Some of you aren't even going to write down that root 48, because you can already see that when you take the square root of 48, well, 48 is just 16 times 3. And so my square root of 48 is really just 4 root 3. And you could have jumped down to that line. In fact, I'm going to argue if you started with the original problem given, you could have jumped to there. That is, I don't think it's a big leap for us to see, hey, we're going to get rid of the minus 45 and then divide out the 3 in one step. I think you're capable of it. Okay, let's keep going with the problem. Now I have to get rid of a plus 6. To do that, I need to minus 6. I can't collect again because of that root 3. So to get rid of a times by 2, I am going to divide by 2. And now, if you got down to that, then I think you were doing outstanding. We're not done yet, though, because that expression can actually simplify. I want to come back to what we talked about before in question D. How many terms do you have on top? You have 2. How many terms do you have on the bottom? You have 1. And if I circle all of those terms, you will see that the whole number in each one of those terms has a common factor of 2. My first term on top is 6, or negative 6. My next term has a 4 in it. It's 4 times root 3. And on the bottom, I've got a 2. That is, all of those values, those 3 terms, have a 2 in it. So I can divide out that 2 from the top and the bottom, and that's going to get me a negative 6 divided by 2 is negative 3, the plus and the minus. 4 divided by 2 is 2, and I still have that root 3 attached. Now, please don't still have a 1 on the bottom. That's us dividing out a common factor of 2, but not realizing that we can simplify that thing. So I'm going to get rid of that minus 1 because of the bad form and recognize that we could divide out a 2 from both of those terms. Okay, if you happen to get down to x equals negative 3 plus or minus 2 root 3, that is great. I think you're really working ahead of the curve. Okay, we've got 2 more problems for you. Okay, I want you to take a look at G and H, and I want to address a situation that's going to arise in question G. And this is a situation that we're going to deal with if we choose to isolate, and something that could lead us down maybe a bad path. We're going to work our way through G together, and you might be looking at G going like, I don't understand, G looks so simple compared to what we've been dealing with. Yeah, but there's an extra wrinkle. Okay, let's quickly go through the same process. I can now divide out my 2, but you might notice that to now go ahead and to get rid of that exponent 2, I take the square root. And when I take the square root, I get this. What's so bad about it? Well, to take the square root of a fraction, I take the square root of both the top and the bottom. Right? A fraction is one term. For me to take the square root of one term, I have to make sure I take the square root of all of its parts. You'll notice, though, that I cannot calculate the root of 5 nor the root of 2. Now you start to say, why is that a big deal? Like, we've had roots to this point we couldn't calculate. The last problem, we were root 48. Really, the problem is it's that root 2 on the bottom. If you were to go through and punch that into your calculator, you are going to see that you get a super ugly decimal pop up on your calculator screen. You're going to get that root 2 value is approximately equal to 1.41421, blah, 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 on and on and on. What you actually end up getting is an irrational number. And if you think back to grade 9 and our discussions about number sets, that irrational number is a decimal that's going to go on forever and not repeat. Okay, why does that become a problem? Well, I want you to think about whether that has meaning or not. You take a peek, and if I had asked you to go ahead and, I don't know, take your 6 pencils sitting on your desk and break them up into 3 groups, you could see that you would have 2 pencils in each group. Makes sense, because your denominator was a whole number. If I ask you to take 6 pencils and break them up into 5 groups, well, I think it makes sense that we're going to have a whole pencil in each group, plus some other bits in those groups. Yeah, we might end up getting bits for our fractions. 6 broken up into 5 groups gives me 1 pencil in each group, plus a fifth of a pencil in all the other groups. But at least that makes sense. Like, you can think about bits of pencils. Well, if I was to ask you, take 6 pencils and break them up into 1.41421, blah, 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 that never repeats, never ends number of groups, you should be looking at me weird. That doesn't make sense. How can I have a number of groups that I can't even define, really? I can't. And so having that root on your denominator causes a problem. So what ends up happening for us? I need us to understand that at our level, we're going to actually end up writing some stuff down that's not fully simplified. That I'm going to ask you that when we go through to take the square root of a fraction, and you see that the denominator is not going to be something you can calculate, then what we're going to do is we're just going to take the square root of the whole fraction. We are not going to take the square root of its parts. So I'm going to erase that line that I just wrote down because I can see what I'm going to put that blue star beside. If I did take the square root of it, my denominator is the square root of 2, and I can't calculate that. You'll also notice if you look back to a in that really long way, I can't simplify root 5 either. And so, even though it's a little unfortunate, this is how we're going to finish our expression for x in equation G. When you go walking into your grade 11 university math class, you're going to learn how to deal with that situation of having an irrational number on your denominator. For right now, that's what we finish with. Okay, with that point clarified, I think you now have an opportunity to work your way through H. Okay, I'd like you to pause the video, give it a shot on your own. I think H should be super fast. Okay, pause the video now. Now, okay, we're back. I'm going to just put a little line through, and I'm hoping you guys can maybe see why I said I think we should be super fast. Okay, I'm going to go through this process because it should feel like clockwork for most of us. Get rid of my times by 3, divide by 3. And maybe we stop there. Maybe we went to the next line to get rid of the squared, take the square root, and that's where we noticed our problem. Okay, that should be screaming at us right now. How could you ever take the square root of a negative number? We can't. Square root is looking for 2 of the same factor. If both of those factors are positive, then that gives you a positive. If both of those factors are negative, that also gives you a positive. You cannot take the square root of a negative number and get a real number. So what do we end up saying for that equation? We would end up saying, therefore, there's no solution. And there's a lot of stuff for us to discuss. We're going to talk about it in great detail in this unit. Maybe you would end up seeing like no real solutions. If you just wrote no solution, I am quite fine with that given our environment. Maybe you can see, though, why I would have said, maybe we could have stopped there and made the statement on no solution. How can I ever square something and have it give me a negative? We may have recognized right on that line with the star beside it that it was impossible to solve that equation for real numbers. Okay, we've gone through a process today about isolating a variable when you happen to have some exponents on it. Your job right now, jump in, get lots of practice. Make that feel like an algorithm. Make it feel like a process you could repeat over and over again. Okay, best of luck.